So what we are going to do is we'll have a understanding of how we are going to have general principles of quantum mechanics. So quantum mechanics, as we know, of quantum mechanics. So as such, when you say principles, means a set of rules from which we can define, thus from which we can describe for a theory, a given theory. So in our case, the theory will be a quantum mechanical theory. So even the very word principle may be because what we are going to do in this thing, the thing which we are going to study this to read chapter 3 of mind. So principles of quantum mechanics. So we are going to have the sort of we are going to follow this chapter by mind. The name of the book is Principles of Lectures on Quantum Mechanics. So maybe it will be in a sense helpful if you can also read some chapters like historical introduction of quantum mechanics before coming to this chapter. But at least to say a bit is that even when we say principles, there are not as such the principles. So here what we are going to do, we are going to see how what is the mathematical way of trying to formalize quantum mechanical principles. You got my point? So what the formulation of those mathematical constructions or structures which will help us to describe quantum mechanics as a theory. So that's the part of that thing. That's the our main thing which you are going to do in this sense. So in the first thing, what we are going to describe is how we describe states. So states, you know, like the way in classical mechanics, we don't talk of states, we talk of evolution of a particle or a system of particle from state A to state B. Whether that evolution can be described as a Lagrangian or an Hamiltonian, or in the earlier classes, how we describe the motion of a particle when some force is applied. And that force will be E field, electric field, gravitation. So the force, so evolution of trajectory of a particle in space. It was a more sophisticated language is a Hamiltonian way of describing a system, but or a Lagrangian of a system, which will describe the evolution of the state of a particle or a system of a particle, and sometimes it may also include the entire universe, the different think of it, the different particles in the universe. So it can. So there are various subtleties to it. How we can describe states. So we don't talk of how the motion of a particle. So we talk of quantum mechanics and states, and states. So there's a fundamental jump in conceptual understanding. Why we move from particles, evolution of particle in space, phase space, or to states. So here, rather than saying what we define states as psi or a wave function, what we are going to first say that a physical states can be represented by vectors in some sort of abstract space, which is also called Hilbert space. So in quantum mechanical way of looking at things, the notion of Hilbert space becomes important. So conventionally, when we go to, if you just take any course in finite dimensional vector spaces, the end part of it is that Hilbert spaces as an infinite dimensional vector space. So once we make a translation from a finite dimensional vector spaces to so we don't define, we have an inverted way of defining infinite dimensional vector spaces, which is called Hilbert space. We define it's a sort of finite dimensional space, but modulo some assumptions. Modulo some assumptions, how we define it. So we just suspend it, how we define the Hilbert space. But the point is that states of quantum mechanics are defined or can they have a representation in that abstract space which is called Hilbert space. Got the point? The way we define the vectors has something called direction and something called magnitude is there, we call it vectors. And that understanding may be more sort of, when we talk of direction vectors, so it's sort of coordinate invariant. So you are not interested in, for example, a vector has some components. You are not interested in from which coordinate system its components are depending on which law. So it's sort of coordinate invariant. So according to Weinberg, so he finds it more convenient or more natural way of describing vectors. But we want to make an analogy of those vectors with the vectors which we define in the Hilbert space, which will correspond to the states, the quantum mechanical states. That's the point. So that's it. So here Hilbert, the way we say vector space is also independent of the coordinate systems in your earlier classes. In the same way, we say Hilbert space is independent of the coordinates we use to describe directions in these spaces. So, from the notion, if you might have some illusion of in wave mechanics, how we define state of a particle. So you have an analogy of wave associated with the way we have group velocity and phase velocity. We don't talk of particle, we talk of how a wave translates with a peculiar combination of phase velocities and group velocities. And here we say if there's a particular thing how that propagation vector is there. So we can say a quantum mechanical state is also, when we talk of a particle, it's not a particle, it's not a wave, it's something called wave particle duality. And within that context, we say a particle at a given point, you cannot localize it at a given point. This is a wave mechanical understanding. So it has some wave elements, it has some particle elements. So where the dispersion is maximum, so it becomes sort of, where the probability, this amplitude is maximum, we say then particle, it's here, here somewhere. So you can say that analogy is there. So within that analogy, we can describe the state, quantum mechanical state, vis-a-vis those wave functions. So and the components, we can say the component psi, which exists in that abstract space psi. And we can, we happen to choose the coordinates. Now the point is the same vector could be described by the wave function psi. And we can define it. So we are going to do some another way. We have not only have momentum space, we have a position space. Okay. No, one is we can describe a normal space the way you do Fourier transformations. You have a space and you have an ambient space. And by inverse operation, you can map a function back to its original space. So you can have an original space and you can have its functionalities associated with some another ambient space. There is always an operation, you can go from ambient space to original space and back. So in the same way, there is also this. We can have a position space as well as momentum space. And in momentum space, we have the wave function psi p momentum is defined as a coefficient of exponential of iota p dot x by h. Iota p dot. So where this exponential is there, we can have cos of iota p dot x by h. It's a sort of wave. It's a sort of sine wave or cos wave both together. That's a sort of complex wave, which will represent that thing, those psi. Got the point? So this is it. And in momentum space, so it's defined in momentum space. We define psi as. So we define psi as it's in momentum space, three-dimensional space, three-dimensional momentum space is defined as how we are going to integrate it. Integrate it means wherever it has gone, the particle has gone in that momentum space. And this is the way we define it. Where psi bar p is regarded as a component of the same space. Component of the same space. The way we have a normal vector has a components. It's not always that all components will contribute. Some will cancel, some will contribute, some will partially contribute. So you have to see it. When we are going to Fourier transform. We are going to see the contribution of this momentum component in that ambient space or momentum space. Got my point? That helps us to, and we are summing the total contribution, the components, how they sum in that ambient space. Just like in a vector, when you have force in a given particle, you resolve the vector particle, which components will contribute, which will not contribute, you do the same thing here. So we can have in 3 dimensions D3 3 dimensions. So now if you define them in terms of wave expansion, in terms of some wave function, psi and x is defined with a definite energy. Psi of x can be defined as Cn psi of nx. Where Cn, you might have seen this expression, where Cn are the components of same vector of same state vector along directions corresponding to a definite value P of momentum. You got the point. So Cn, so if just psi n is a general function, if you are going to see Cn, n can vary from 1 to 2. So these can be different components which are associated with this wave function psi.
Yes, so wave function is our state vector.
Yes. Cn may be the components of the state, which can take value 1, 2, 3, and total addition will give us the total wave evolution of the total wave function of
it. Only one.
The state vector is which state vector?
Psi.
Psi is one. Yeah, the components of the psi.
Yeah, there could be many.
There could be many, which is described by this Cn. Cn can be C1, Psi1, C2, Psi2, C3, so on and so forth. Yes. Now we are, so this much is clear. So now we are coming to our how we are going to have the description of Hilbert space, which will correspond to How we define Hilbert space? We normally say Hilbert space. So there is a mathematical way of defining, rigorous way of describing a Hilbert space. But now sometimes what physicists do, they make some of the definition mathematicians more a bit malleable. They somehow they change those definitions to suit their things. So they may not be that rigorous sometimes. So they change sometimes those. So we are not, even this Weinberg book, he has not defined Hilbert space in that rigorous sense. So if you go to any fundamental book, for example, Helmholtz, you can see at the end, flap end, he has given the description of Hilbert space. So that's the beginning. So the point to mention is how, because our interest as physicists is not, we are interested in the physicality of the world and how we want to a representation of that physicality, of that wave function psi, and how we can formalize them in some mathematical principles. This is our beginning. That's the point. So in that context, so Hilbert space is a kind of normed complex vector space so any sort of quantities, so it's a sort of norm vector space and non-complex vector space. Nor means, basically we define it as we have a self-adjoint inner product, which is norm, and in those self-adjoint inner product, one is the complex conjugate of it, such that when we have an inner product, so it will get square of that the thing. The inner product will be square of that thing. It may be greater or equal to 1. That's the precise. So it's positive definite, semi-positive definite. And there's a particular that Cauchy theorem. So there's a Schwarz identity to describe that. So if it's a non-complex vector space, and in general, for example, any sort of vector space consisting of quantities psi prime. So if psi, so now we are coming to the property. If psi and psi prime are vectors, then so if you change the order, then psi prime and psi should also be vectors. So if you want to say, if you change the order of the psi and psi, so it should not affect the thing. It should not affect the properties. The way we define have properties in normal vector space. We have linearity property, we have associativity, commutativity, and other properties. So in the same way, so you can, if you change the order, for example, psi of psi plus, for example, psi prime should be equivalent to, if you change any order, it should be psi plus psi prime plus psi. Yes. So you can change order, it will not matter. Or you can, so it's for three states. So for 2 states, psi prime is equal, in the simplest case, should be equivalent to psi. Now the second property is that, for example, if psi is a vector, and alpha psi is any number, alpha psi, so alpha is any number, or alpha normally talk of, it's a scalar, it's also scalar, or it's a number. Then in the complex vector space, in Hilbert space, we normally talk of complexization. It's not a normal space, it's a complex vector space. And there can be vector spaces which may be real as well as complex vector spaces. So it's an exercise how we can complexify a real vector space. Or from a given real vector space, complex vector spaces, how we can come at it can be a subset, you can arrive at real vector space. So it's also an exercise in this thing. But here we are going to use these properties. So here either, for example, real or complex vector spaces. So multiplication by number is taken to be either associative or distributive. So that there is a property of associativity as well as distributivity. So if you want to enumerate them simply, if I enumerate them simply here, or I'll just so alpha into alpha prime into psi. So you can change the order. You can see, you can take them in brackets. It should not matter. Here you multiply first the scalar with this wave function. Whatever you get, then you multiply it with this scalar.
Or it doesn't matter.
So what he says that if you multiply the two scalars first,
Then multiply
it should not matter. So the statement says, for example, if you multiply the scalar with this, so whatever you get the group, then you have to multiply it with this another number. So if you, because sometimes it's not necessarily true. If you multiply a certain quantity, physical quantity with some number, it will change. And once you change it with some another thing, so by changing the order, so if you multiply a certain number with certain other thing, it may change as a quantity. And then you multiply it, it will further change. It will not change if you do it in the reverse way. If you multiply two numbers together and then multiply it by a certain quantity. So you try to understand it that way. So it's not, they look simple properties, but to emphasize, that's why we are trying to emphasize it. Because in quantum mechanics, the linearity property is not entirely commutative. So that makes the difference in entire things. So in the same way, the second property is alpha psi plus alpha psi prime. Again, and alpha plus alpha prime into psi should be equivalent to alpha psi plus alpha prime psi. No? So this is it. Again, this is this much. This is third. Now the fourth property you can say is that. So this is a single zero vector, zeros with obvious property such that 0 plus psi is psi.
Zero is called identity.
But it should not matter. So it's or a scalar into 0 should be equal to 0. Now we are coming to the properties of linearity. So properties of linearity, you can say that. So a normed vector space, vector space for any two vectors psi and psi prime, there is a number. So the scalar product psi prime with properties of linearity property क्या है? What's the properties of linearity? In the properties of linearity, we can have superposition is not in that. So you can say if we define psi and psi prime, so the properties of linearity are like this. If you define as alpha prime, so So there are different ways of stating the same thing. So if you have an inner product of psi prime double prime this, so how it is going to multiply the thing? So it should be equivalent to like this. You can take the scalar outside and multiply psi double prime with psi, or you can take the scalar outside alpha prime, then you have inner product of this and this. So this linearity property it should hold. If you have an inner product of psi double prime with this quantity, the scalar should come outside. The scalar should multiply with both this and this, and alpha prime should multiply. You can get scalar outside these two. So this is the property. And there is also a property of symmetry. And symmetry means psi star. So if you have a complex conjugate of it, so for example, if it's an inner product space psi and psi star. It's an inner product. One is a complex conjugate, another is psi. That's why we call it inner product space. It's a complex inner product space. So if you have a conjugated psi conjugate, it will come psi back, and it will be psi prime. Okay. The second one was not conjugate, it became psi star, and it became double conjugate. Psi conjugate, it became psi prime. And the other property which we talked, the inner product of psi star or psi. Here it will be 0. Here's talk of 0, but we will talk of the precise criteria. It's greater or equal to. It's positive semi-definite. It's what is also called for psi not equivalent to 0. So in the same way, we can have psi of 0 will be 0 for particular psi is 0. For any psi. And in the same way, alpha of psi of 0, how much it comes? So you can define it. So you can also write it as, got the point? So you can, scalar you can multiply it by the scalar, and you can change the shift, this thing. And at the end, it will also, you can also write it as psi of 0. Sorry. Now again, you can have from this, if you give values, I have not given the numbering to this equation. If it is 3.17 and if it is 3.18. So if you just use 3.17 and 3.18, so using this, you can rewrite this identity as, you can see it as a small exercise, alpha psi plus alpha prime psi prime psi double prime is equal to alpha star. So we'll just have this psi star plus alpha this plus alpha prime psi star. How you can honor this? Yes, exactly. Now the thing is that you can change it. For example, if you do one step more, you can have this conjugate. It will be here, and if it will not remain conjugate, this will remain conjugate. It will not remain. So the book has written it this way. It is applied to those operations here. So you can write it here like this. So how much time? So okay, just we have time. So now the question is how define the linear dependence and linear independence of the vectors. It might be also. So traditionally you say linear independence is alpha 1, x1, alpha 2, x2, alpha. So such that alpha 1 is equal to alpha 2 is equal to 0. And linear dependent is that in which alpha 1, alpha 2 may not be necessarily 0. But it's always easy to find from a linearly dependent set. You can have as a subset some linearly independent vectors. So the game here becomes how we can use this construction of linear independence and linear dependence in our construction of these Hilbert spaces. If you define that wave function psi as these elements in terms of finite dimensional vector spaces or linearly independent vector spaces or linearly dependent vector spaces, how we can translate this language here. So this is our next thing. So for linearly independent or linearly dependent, so for example, if psi 1 and psi 2, psi 1 and psi 2, psi 2 are said to be independent if no non-trivial linear combination of vectors vanish. Vectors can said to be independent. No non-trivial linear combination of vectors should vanish. So this is one thing. So if psi 1 and psi 2 are linearly independent, then we can have alpha 1 psi 1, alpha 2 psi 2, so on and so forth should come out to be 0. Such that alpha 1 is equal to alpha 2 is equal to this is the way we define things. So, or one set of independent vectors can be expressed as the linear combination of the others, because at the end you can say all of them come out to be 0. So you can express one in terms of others. That's it. So from this, now the question is, in particular, for example, set of vectors psi 1, psi 2 are independent if they are orthogonal. So orthogonality as a condition, you have seen it. Orthogonality in, for example, dot product cos of 90 is, so you can see it. So if vectors are independent, they are orthogonal. Got the point. That orthogonality and independence, they are perpendicular to each other. So if it's one, it's perpendicular. So for that, you might have there are different ways of writing. One is orthogonality, the other is orthonormality. So orthonormality alpha ij, for I is equal to j and I not equal to j. If I is equal to j, it's 1. If I is not equal to j, it's 0. So in the same sense, so psi I, psi j is equal to 0 for I is not equal to j. This is the way we write this orthogonality condition. Orthogonality is a set of conditions for a set of vectors which are going to satisfy this condition: alpha 1 psi 1 plus alpha 2 psi 2, so on, and it will come out to be 0. And if we have a scalar product also, so alpha I, psi I, psi I, it will also come out to be 0. Or if it's 0, this means the scalar will also come out to be 0. From this. Either this will be 0 or both will be 0. So we can adjust. And the question is the converse does not hold. Converse does not hold means what? So if they need not to have to be orthogonal, then what? Such that if 1 is less than, I is less than or equal to, and if they need not to be orthogonal, then there will always find n linear combinations of phi, n linear combinations of phi of these vectors that are not only independent but also orthogonal. What do you mean by that? So can you think over it? So what he wants to say? The converse does not do not have to be orthogonal. So, for example, it's not the converse also. It's not necessarily they have to be. So you can construct this thing whether it's orthogonal or not. If it is not orthogonal, so how will it be linearly independent or not? The condition of alpha 1, psi 1, alpha 2, psi 2, will it be necessarily equivalent to 0 if it is not orthogonal?
In the process called denormalization.
So this is a procedure. How we can? So if it's not an orthogonal, so whether linear independence as a condition should hold or not. So this is the point. What the point? If we have a non-orthogonal construction, whether linear independence as a condition should hold or not. This is the question he is trying to. So it will lead to some. So we'll suspend it for some time. Whether we can construct a non-orthogonal transformation, whether it will be linearly independent or linearly independent. So this is the point which you are going to see. So before we are going to address it or we are going to say something about it, we are going to define something called complete. There is something called completeness condition. So they are all related terminologies which will start. For example, we say in Hilbert space, it's finite as well as we normally say it's infinite, but we can say it's sometimes finite, but it's complete. So you can always construct a finite dimensional Hilbert space from an infinite dimensional Hilbert space. So we sometimes make one of the assumptions malleable. So you can have a Hilbert space can be constructed from a finite dimensional space provided it is complete. So we leave that. But here, what we are going to see is that a set of vectors psi 1, psi 2, psi n is said to be complete. Complete if any vector can be expressed as linear combination of psi. Psi. So set of vectors is said to be complete if any vector can be expressed as linear combination of psi I, such that psi can be defined as alpha I1 psi 1, alpha 2 psi 2 plus alpha n psi n. Now we are going to we are going to address this question. For example, the vectors of complete set do not have to be independent. So the vectors of complete set do not have to be independent. So if they are not orthogonal, so we asked if they are not orthogonal whether they have to be independent or not. So the answer here is the vectors of a complete set do not have to be if they are not orthogonal.
If they are not.
If they are not orthogonal. So this follows. So we can always find, now purchase, we can always find a subset that is both complete and independent. But how? By deleting any vectors of the set that can be expressed, that can be written as linear combination of others. So the point is, so we can always find a subset that's both, it's also both and independent. So if it's not independent, for example, if it's not orthogonal, it may not be necessarily linearly independent. So it is linearly dependent. But from that linearly dependent configurations, we can always find a subset which is linearly independent. Got the point? Which is complete and independent. And what we can always, which can be written as, we can delete them by writing them any vectors as a set, as a linear combination of the out of that. So you can do it as a procedure. Okay. So this is the point. So we'll stop at one sentence here, and then how in the next we are going to see some more properties. So the thing is that given a complete, so I'll just write a statement, given a complete set of vectors psi by the methods which have been described, We can find a set of vectors phi I that are orthogonal as well as independent. So since according to this construction, every psi is a linear combination of phi I and phi I are also complete. So now, given a complete set of vectors psi, we can find a set of vectors phi I that are orthogonal as well as independent. So now we are coming to this thing. So given a complete set of vectors psi, you can find a vectors phi that are orthogonal as well as independent. This is fine. So every psi I is a linear combination of phi and phi I, which are also complete. Now we will come to the way we have defined Hilbert space here. So a complete set of orthogonal vectors is said to be basis for Hilbert. So we are stopped. So we are going to say, so we are coming to the basis from which Hilbert space are constructed. The way normally we say matter is composed of atoms, electrons. What are the fundamental building blocks? So if you linear space, vector space or finite dimensional vector space, it's something from which we are going to construct some states, and we are going to map them to some physical state psi as a wave function. How we can construct that basis space in such a fundamental level? So we have arrived at a definition of Hilbert space. If there is an orthogonality condition holds, a set of orthogonal vectors, a complete set of orthogonal vectors is said to be the basis of Hilbert space. So we are going to continue this Hilbert space.